Hello, this is John Wayne. The title of the talk is 3D to 2D to 3D conscious learning. I will talk about why conscious learning and a single framework for different tasks, including AI bottleneck tasks like vision, audition, natural language understanding, and navigation. The first general purpose machine thinking model that are based on Turing machine, but uses motor imposed learning mode. Then the first machine consciousness model is also based on Turing machines, motor imposed teaching. Then the first 2D to 3D machine consciousness learning model without motor impositions. Number 6, conscious learning theory. Number 7, autonomous imitation as general purpose method and analysis of the and concluding remarks. Based on Merriam-Webster dictionary, consciousness has 5 levels of definitions. State of being aware of something within oneself, external object, state of fact. Then there is state of sensation, emotion, volition, thought, totality of conscious state of an individual. Number 4, normal state of conscious life. Number 5, up state of mental life of which the person is aware. So consciousness is defined at least 5 levels, and our definition of consciousness including all. Why conscious learning? In 2008, Xiao and Yicheng published in Current Biology an interesting result about perceptual transfer. And I think that's the evidence of conscious learning that takes place. So the experiment has a 90 milliseconds exposure of the stimulus at up left, then repeated again, and that for different days with more learning, the response was improved. But for the red part, which was lower left, was only primed, but not actually learned. But that performance is also improved. Transfer in terms of location that was not learned, but only primed. But the same improvement did not happen for the horizontal locations that was not primed. So the key idea is that this transfer in terms of location for the event, for the double learning on this one and this one, so double learning was improved, but not generally, not for other locations. So conscious learning is necessary for learning. It's not individual images that learner is conducting, but rather consciously look at the context. And in this case, prime was this event, and not isolate image frames. And the human think while learns. So learning is conscious. So here is an example of how kids learn their attention. And there are other things kids can attend to. Teacher is showing something, kids is paying attention to another place. So learning is autonomous. But in current situation, big data has been widely used in brute force machine learning, where the just doing data fitting. But this kind of big data violate what I call sensorimotor recurrence. The next sensation depends on current action. With big data, you don't output any action, and the next frame is assumed, and assume that a machine does not make any mistake, but machine does make mistakes, all right? Or explore the other situations like previous example. And all public available data sets are flawed. In addition, I will talk about another thing, which is the protocol flaw. Since 2015, all AI papers in Nature has a severe protocol flaw in the sense that there are many networks that are tried, and then every network is greedy and a local minima, and they use the test set to pick the luckiest one. But if you use the validation set, then the luckiest one will not perform as well. So that's a very severe protocol flaw that leads to a misleading results. People say you want to compare with their work, right? So I already compared the luckiest backprop compare with our optimal. We just need one network, developmental network. And we already reached, in this case, as with the well-work training, and brute force will not do as well. And we have well-work training is much lower in error. But the luckiest network is very slow. That goes through the data, 10 epochs still there, but you need at least many, like 500 epochs of through the data, but still not as good. So let's talk about the single framework, not deep learning network that many people are aware of. And I'm the first person that published a deep learning convolutional neural networks for 3D work. And for the material here that you probably want to read the book available at Amazon, it talks about 3 kinds of tasks. And most of the tasks that we are having observing machine learning is clean tasks. And conscious learning is able to do very muddy tasks. Developmental network, it's a highly recurrent network, a deep network, but it's not the cascade. At motor area, the areas are concepts, more motor and more abstract. And early neurons are more concrete. And there's no convolution used here. Each neuron has a bottom-up connection, has top-down connection, has a lateral connection. Then you consider all the neurons, then each neuron also do effect, top-down effect, lateral effect, and bottom-up effect. So end up with 6 fields. And I will talk about this formulation later. And this network can also get output from the motor area, in this case, the location and the type. Then this area, this is like motor area or premotor area, then can lead to relations like A-B objects to A-B object. That's a relation between A and B. So you can build a conceptual hierarchy. So I just briefly mentioned our experimental work on this particular paper in ICCE 2022 does not have space for experimental work, but I'd like to mention our experimental work in this talk. So we have a vision, they have a stereo camera. Zhao, he did a PhD at the MSU, and he learns a network in a mobile form, deal with natural images and with attention. I talk about attention later on. And a very challenging tasks include the lighting, shadows. The blue part are trained, red part has a lateral connection. It's like syncing, with lateral syncing, white-to-white connections. And real-time testing is the purple one. So you can see that that's disjoint test. So the many concept learned. And we also learned parking. And this is the audition. And we have frames, very dense frame, like 20 milliseconds per frames. And we have a mode of cochlea and a tip cochlea sensitive to the lower frequency, and base of cochlea has sensitivity to a high-pitched sound. We also develop a motor through the sound. Here, you hear the sound, you develop motor area, and the motor area will co-develop with hearing experience so they can make voice, because the generative synthetic sound is difficult, and we use principal component analysis to develop sound. Then when you speak, you have to have dense labels. The language part we learned a lot in the bilingual environment, English and French. And this is the representation here, the representation in the context of meaning. And this is the representation coded in the text of the neutral, French, and English. This is the maze navigation, and the agent move around the different maze, and it has images, detect the environment, and learn basic skill from going around and different settings. And then select route as a plan. There's a longer sequence later on, same network, learn different routes. and it will learn how to count the distance, then how to select the best route. And because the network has a power to the abstraction, instead of brute force, deep learning networks doing pure data fitting, and the success rate on the new environment, totally new environment, reached 100% accuracy. This is the power of abstraction. Then you need the body, and body allows you to interact the real world. So the first general purpose thinking model, we need to talk about the Turing machine. Although Turing machine is not for neural networks, but the ideas are very useful for us to understand the neural network. So it's a unification of symbolic network, which is Turing machine here, to the connectionist framework, which is the neural networks. So the traditional FA, you have a state and you have output, all right? Then our agent FA, the output state directly. So each state will transition, then 0, 1 in this case is the input symbolic. And then you have a sequence that take into account the context, and agent network output the state directly. And we also do the attention. Turing machine does not attend anything, just take symbol at a time. When we have images, we have different parts of the patch of the image. For example, car 1, car 2, and you have a partial of the car, partial of the sign, and partial of the pedestrian. So attentive FA, the control of the Turing machine is not only an agent FA, but also attentive agent FA. And I'll talk about attentive agent FA when we go to network. And the Turing machine has a tape, has a read-write head, and a state transition table. And for our network, the tape becomes the real world. Read-write head becomes camera and effectors, and the transition table becomes neural network. And a Turing machine originally takes a special purpose and known a particular task that you design a transition table according to the symbol in the tape and one symbol at a time. We have a 5 tuple for Turing machine: state, tape symbol, new state, output tape symbol, head motion. But the universal Turing machine is impressive in the sense that input is not just data, but also programmed in the sense of 5 tuple: state, input, next state, output symbol, and head motion. So a sequence of 5 tuple is like 5 words, sentences, and then the machine is able to simulate this program. So the fundamental difference between regular FA, which is the regular Turing machine, which is special purpose machine, to a universal Turing machine, is that the input has 2 parts. One is data, another is a program. So without knowing the task, originally you know the task, then you design a task-specific program, so special purpose. But universal Turing machine, you have a human-designed program. But if we think about the tape becomes the real world, then everything in the real world is a program too, including classroom teaching. So then we have a network here, become general purpose. So control of Turing machine is FA, and I will not go through the proof. I will encourage you to read the IGSRS, International Journal on Intelligence Science. And basically, you need to consider the context as the input, then it becomes the FA. And if we consider context as input, then the input can have X, Y, Z. The network has 3 areas, X, Y, Z. And Z is the actions, X is the input, and then the Y is a hidden area that has a competition, and the top point competition in this case is easier to understand. Each neuron has a bottom-up input, is a global input or local input. So if this neuron win, as here, pay attention to the local patch. And if you this neuron one and do the global patch, or you can have a different location of the patch, different feature of the patch. So it depends on competition. The winner will lead to different attention. So attention is a competition, and attention competition is based on not just bottom-up input, but also top-down input. Top-down is the context, and the winning pattern in the Z is the context. This is like FA. Winning context is the current context. Then the winning neuron will take care of the current sensory input and current context input, and both go to next one. So once you fire, then heap learning in the internal wide neuron, also heap learning in the motor area, and everything is heap learning. So all the learning is unsupervised, although motor can be imposed. All right, so it's a very new concept, and this is very different from symbolic network like Markov decision process and deep learning, and everything is a class label, for example, that's a symbols. And once the features converted into symbols, then become symbolic transition tables. And here example that if you have a particular task, 1 and 3, and you have a grand transition table, and they present each state as a binary symbols, binary patterns, like a spiking neuron firing model, and input is all binary images. Then if you use binary patterns, then you don't have any symbol here. All right? So it's very interesting that you do have understanding if you have original symbols. But once you have a binary patterns, then you don't need a symbol. So the emergent grand transition table, fully automatic. So let's talk about the 8 properties. GENISAMA is the acronym for 8 properties: grounded, emergent, natural, incremental learning, skull closed. Why must be skull closed? Every learning is fully automatic. And with competition, deep learning does not have a competition. Right? And attentive, motivated, abstract. Neural net do not abstract well. So all the neural net you are familiar with, like cascade neural nets, they don't abstract. So abstraction allow you to do imitation. So we need a platform, and GENISAMA is also name of the small startup that I helped to create, that you can have a see what the robot see, and this is a wearable robot. They can teach the robot in terms of action. In this case, with real-time and incremental learning of disparity. In 2021, also we learned the actions with the disparities. And this example of thinking in a navigation case, that how does a planning? You can have a forward, that you can learn turning around, and turning left, avoid obstacles. Then you can take different routes, route 1, routes 2. Then you learn how to compare the cost of routes. This is thinking. Then you pick up the task that has a lower cost. Then you carry out. Machine conscious model require 8 properties that are all necessary for consciousness C. And conscious machines, I published basically consciousness must be learned. Consciousness is not just outcome, but also the causality of learning. That's the essence of conscious learning. In order to reach general purpose AI, you must do conscious learning. It must causality. Now, this new in the paper is 3D to 3D. And you have a 3D word. Then you generate 2D images, and you generate also motor images. That's your program. So motor muscle is in 2D, just like cochlea, like your motor cortex that are 2D primarily. Then you back to 3D. You incrementally learn, then you generate the muscle actions, then you try and error. In a kid's case, you try to reach, pre-reaching, and you become more and more dexterous. And without using inverse kinematics, because you have a redundant arm like our hand, and you don't need to really do computation inverse kinematics like traditional robotics. And then the skill is generated incrementally, get refined over age. And we can avoid learning things like task-specific demo. So talk about conscious learning theory, no symbol at all. You need a minimal set of mechanisms that we already found based on Turing machines and universal Turing machines. And an emerging model for holistic consciousness, detailed level 2 computation. We have a complete algorithms that can be implemented, detailed overarching model for all kinds of consciousness. Small or large brain can be also implemented and tested. The higher level consciousness need to accumulate through time, through age. So lifelong conscious learning for higher consciousness. So definition of consciousness is a conscious learning by a biological or artificial machine, basically biologically modeled also, is that a learner is conscious throughout the lifetime learning. It bootstraps its consciousness from default consciousness right after birth, that's subconscious from the prenatal development, and increasingly conscious to maturely conscious. GENISAMA are all required, and conscious learning has the 8 conditions of GENISAMA, but in addition, also need to have a real time. For an emergent universal Turing machine, you need an emergent Turing machine in addition to 8 conditions. So we have a SEB representation, S for skull internal representation, and 1 if it's not symbolic, not supervised. If it's symbolically supervised, 0 means emergent, E for effector imposed, 0 otherwise, B for biosensors used. Biosensor is like pain, sweet, all right? And if you use a sweet or pain, that's 1, otherwise 0. And the enable is a binary code SEB, and this is from the environment. And this is the 1 page for formulation. So state, input, originally you have a transition of, this is a FA transition, and we already said a corresponding Turing machine. Then emergent representation, instead of symbol, 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 we have a vector, 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 motor vector, sensory vector, and the next motor vector. But this is without internal representation. For the brain, you need internal representation in order to have a competition, and also you need to do interpolation, all right, generalization. So Y is the internal representation, and in unfolded time, hidden Y, fully automatic computation and self-organization and connection inside. And then in unfolded time 0, 1, 2, and we represent X, Y, Z as S0, S1, S2, then you end up with state transition, all right? That is not a state anymore, it's called a context transition. So from now on, we only understand the context transition because context has X, Y, and Z. So very, very neat mathematics. Very beautiful, and the connection of each neuron connecting the part or totally depends on the statistics using Hebbian learning. And then we have unfolding time, you can do auto programming for general purposes inside the DM, and you have a sensible word and a sensor X, skull brain Y, motor Z, actable word W, and the time unfolds. Everything is a beautiful mathematics. Then we talk about how we do competition inside Y. All right, every Y and Z area, you have individual neuron that detect local components like clustering. And depends normalization, you have a different kind of clusters. CCI, PCA, C for candid, C for covariance free, I for incremental. And then it reached, this is the observation coming in incrementally. And this is the estimation of the feature vector V, and suppose you have a C neuron, and you do optimal estimation incrementally for the neuron area, then the predicted X and the difference between the sensory X and the predicted X is minimized. And this X, including both sensory input and motor input. LCA is the most efficient estimator, and the top K computing is extremely important. Deep learning does not have a top competition, and we have competition This is top-down match energy and bottom-up match energy. And this is without lateral connection, but our network also has a lateral match connection. So once you have an internal generation of the Y neuron and you have lateral connection, you have lateral weights. And the random seeds give the same DM. Here, each neuron has a retention rate and a learning rate. When H equal to 1, learning rate is 1 and retention rate is 0. They have randomly initialized the weights, and although random weights will determine which neuron win, but whoever the winner will take the input right away. So it's independent of the random initial guess. We have always the best maximum likelihood network, regardless of the random initial guess. And then we translate into the GENISAMA optimality. Originally, it's each neuron optimal. Now we have a GENISAMA Turing machine to be optimal based on the 3 conditions. First condition is the incremental learning framework. Second condition is the learning experience and dependent learning experience. And number 3 is the resource. The amount of resource is limited. Autonomous imitation as a general. And by definition, you need a conscious learning agent and action sequence imitates 3D events. It will generate by the conscious learning agent. And the human expert look at the output from the robot, the way that's good or failure. Okay. Good means it's similar. I'll give you example next, all right? And autonomous process, if the effectors are not teacher imposed. Here example, right? The kids, a teacher will hold a hand place a form on an ear, and child will place her hand on the form on her ear. The creativity, there are several creativity I just mentioned too. Teacher becomes self, left hand becomes right hand. Why imitation? The theorem said that will make teaching manageable. Otherwise, it's out of hand, all right? Imitation reduce teaching complexity. Suppose you have n stages, n variation, and S receptive field size, and you have B neurons. Brute force data fitting like brute force big data, you have M to the N training samples and M to the N SB computations. But mode to imposed has only MN supervisions and MN's SB computations. If you do imitations, you only teach one example. That's M equal like one example. And the learner will do practice as a homework, that's imitation. Then same amount of computation. This example, suppose I do one demonstration in class, then other variation was covered by student as a homework. Suppose I give example, suppose innate, I cry. I hear my sound, this is the X effect. Physically, once I cry, I will hear it. Then once I hear my crying and I'm doing crying, this is the motto. So that's the originally Z to X, now X to Z. That's through the brain. Originally it's from physics, now through the brain. And then later on, if I have another baby that also cry, right? This cry very similar to my cry, then I will also cry. That's imitation. Very interesting. So once you observe the baby cried in the entire room, all other baby will cry. That's imitation. But later on, the same thing will happen. Same thing will happen, the complexity becomes more and more complex. It's not motor imposable. Early on, you can do this one using prenatal teaching example, right? Or single kicking and single sucking of the mouth and crying. But the later motor becomes more complicated. But the formulation is still the same. X to Z to X and to Z become X to Z. Same thing here, right? Because the motive becomes more and more complex and has attention going on. and you pay attention to particular sensorimotor area, that's so complex, not possible to be motor imposed. For example, you cannot impose my way of talking. Generality of creativity of imitation, the theorem says that thoughts by a natural or artificial agent through autonomous imitations of 3D real-world events are of general purpose, according to universal Turing machine, right? If you're interested, you look at the proof. If imitation result is judged considerably different but creative, such autonomous imitations corresponding to creativity of the agent in judge's eyes. So although we did not talk about creativity explicitly, but the framework of imitation already kick off the magical wheel of creativity, all right? And creativity was sometimes error, but sometimes error can be verified, or it's just guess that leads to creativity. If it's verified, it becomes discovery. Conclusion: a complete theory for general purpose, Turing machine-based imitation that has 3 components: learn from 3D events, and creatively generate the 2D motor programs, then carry out the 2D motor program in 3D, and all 1 to 3 carry out in real time. It does not have to be in any batch fashion. And a major advance is with the motor imposition, free of annotations. We do not have to annotate images like brute force machine learning. It's a paradigm shift in AI, and learning is totally autonomous. Human-like autonomous learning is theoretically sound. Now, I'd like to mention the future challenge, and also in engineering, it's doable, but a lot of work. It's a brain-size brainoid chips. That's my coined word, brainoid, and learning at high frequency. Thank you very much.